Merry Christmas, everybody! Apache Storm is a distributed real-time computation system for processing large-scale streams of data. It is fault-tolerant, scalable, and highly reliable, making it ideal for processing unbounded streams of data in real time. Created by Nathan Mars, Storm simplifies stream processing by abstracting the complexities of distributed systems. For more tech interview materials, please visit our website bowsy8.com. Core components include 1. Topology. The logical flow of data, similar to a map-reduced job. It consists of spouts and volts. 2. Spouts. Data sources that emit streams of data into the topology, e.g., reading from Kafka, databases, or APIs. 3. Bolts. Units of computation that process, transform, or aggregate data streams received from spouts or other bolts. 4. Stream grouping. Defines how data flows between spouts and bolts, e.g., shuffle grouping, fields grouping, or global grouping. 5. Nimbus. The master node that coordinates and distributes tasks to workers. 6. Supervisors. Worker nodes that execute tasks assigned by Nimbus. 7. Zookeeper. Handles cluster coordination, maintaining distributed state across nodes. What happens under the hood? 1. Defining a topology. Developers create a topology with spouts as data sources and bolts as processing units. This topology is submitted to the Storm cluster. 2. Data stream processing. Streams of tuples, data records, flow from spouts to bolts, where they undergo transformations or aggregations. 3. Task execution. Nimbus assigns tasks, spout and bolt execution, to worker nodes managed by supervisors. 4. Fault tolerance. If a worker node fails, tasks are reassigned, ensuring no data loss. 5. Parallelism. Storm supports parallelism by assigning multiple instances of spouts and bolts to process data concurrently. Example use cases are real-time analytics, monitoring user behavior on websites or analyzing IoT sensor data in real time. Event processing, fraud detection in financial transactions by analyzing real-time data streams. Data pipeline transformation, real-time ETL, extract, transform, load, for cleaning and enriching data streams. Alert systems, triggering alerts for predefined thresholds, like server health or network anomalies. Advantages include 1. Real-time processing. Processes data with low latency, ideal for time-sensitive applications. 2. Scalability. Handles massive data streams by scaling across distributed clusters. 3. Fault tolerance. Automatic task reassignment and state recovery in case of failures. 4. Flexible data model. Supports complex processing logic through customizable spouts and bolts. 5. Language agnostic. Topologies can be written in various programming languages, including Java, Python, and Clojure. Limitations include 1. Complexity. Requires deep knowledge of distributed systems to design and optimize topologies. 2. Resource intensive. High resource consumption for maintaining low latency processing. 3. Outdated ecosystem. Newer frameworks like Apache Flink and Spark Streaming often overshadow Storm due to broader feature sets. 4. Limited state management. Lacks advanced state management capabilities compared to modern stream processing systems. Thanks for watching. I wish you a Merry Christmas and Happy New Year. For more tech interview materials, please visit bowsy8.com. Merry Christmas, everybody! Apache Phoenix is a relational database layer built on top of Apache HBase, enabling SQL-like queries over HBase's distributed data storage. It translates SQL queries into HBase scans and provides relational database features such as joins, indexes, and transactions. Phoenix is optimized for low latency, high-throughput transactional workloads, and integrates seamlessly with the Hadoop ecosystem. It is widely used in applications requiring SQL-like querying capabilities over NoSQL databases. For more tech interview materials, please visit our website bowsy8.com. Core components include 1. HBase as the backend. Phoenix stores data directly in HBase tables. It uses HBase's scalability, fault tolerance, and distributed architecture for data storage and retrieval. 2. SQL Query Engine. Converts SQL queries into HBase API calls. Queries like select, insert, update, and delete are supported. 3. Secondary indexes. Allows indexing on columns for faster query performance. Both local and global indexes are supported. 4. Transactions. Implements ACID, atomicity, consistency, isolation, durability, properties for transactional processing using HBase. 5. Integration with Hadoop ecosystem. Works with Hadoop tools like Apache Hive, Pig, and MapReduce for analytics and processing. 6. Phoenix Query Server. A stateless server that allows JDBC and ODBC clients to interact with Phoenix over HTTP. What happens under the hood? 1. Data storage. Data is stored as rows in HBase tables, where the schema and metadata are managed by Phoenix. 2. Query execution. SQL queries are parsed by Phoenix into a query plan. Phoenix translates this plan into HBase API calls, leveraging HBase's native read and write capabilities. 3. Indexes. Indexes are stored as separate HBase tables. Queries use indexes for efficient lookups, reducing scan times. 4. Schema management. Phoenix manages table creation, schema updates, and metadata synchronization. 5. Optimization. Query optimizations include predicate pushdown, column projection, and index utilization to minimize data transfer and improve performance. Example use cases are IT data management, storing and querying large volumes of sensor data in real-time analytics, use cases like fraud detection or tracking website metrics, enterprise applications, applications needing SQL query support on large, distributed datasets, data integration, querying and combining data across multiple systems in the Hadoop ecosystem. Advantages include 1. SQL over NoSQL. Provides familiar SQL syntax for developers while leveraging HBase's scalability. 2. High performance. Indexing and query optimizations ensure low latency operations. 3. Transactional support. Enables ACID transactions for critical applications. 4. Integration. Works seamlessly with Hadoop tools, enabling hybrid analytics workflows. 5. Scalability. Leverages HBase's distributed architecture for handling massive datasets. Limitations include 1. Dependency on HBase. Performance is tied to HBase's efficiency. Misconfigurations or issues in HBase can impact Phoenix. 2. Learning curve. Understanding HBase and its interaction with Phoenix can be challenging. 3. Limited advanced SQL features. While it supports basic SQL operations, advanced features like complex subqueries might not be as optimized. 4. Operational complexity. Requires careful tuning of HBase, Phoenix configurations, and underlying hardware for optimal performance. Thanks for watching. I wish you a Merry Christmas and Happy New Year. For more tech interview materials, please visit bowsy8.com. Merry Christmas, everybody! Apache Helix is a cluster management framework designed to manage the lifecycle and partitioning of distributed systems. It helps developers build and manage highly available, fault-tolerant distributed applications by automating common tasks such as resource assignment, state transitions, and fault detection. Helix is widely used in systems requiring dynamic cluster management, such as distributed databases, stream processing frameworks, and search engines. For more tech interview materials, please visit our website bowsy8.com. Core components include 1. Clusters. Represents the entire set of nodes and resources managed by Helix. 2. Participants. The nodes or processes that serve data or execute tasks. They communicate with the Helix controller. 3. Resources and partitions. Resources represent logical data units or tasks. They are divided into partitions to distribute across participants. 4. Helix controller. a central component responsible for resource allocation, state transitions, and managing cluster changes. 5. State models. Defines valid states and transitions for resources. Common models include master-slave, leader-standby, or custom-defined models. 6. Helix Manager. Manages communication between participants, the controller, and the cluster's Zookeeper-based metadata store. 7. Zookeeper Integration. Helix uses Apache Zookeeper for metadata storage, coordination, and leader election. What happens under the hood? 1. Cluster initialization. Developers define a cluster, specify resources, partitions, and assign a state model using configuration APIs or files. 2. Controller operations. The controller continually monitors the cluster state, ensuring that the actual state of resources matches the desired state. 3. State transitions. State transitions for resources, e.g., assigning partitions to nodes, are managed automatically based on the state model. 4. Fault tolerance. If a participant fails, the controller reallocates its resources to healthy participants. 5. Scalability. As new participants or resources are added, Helix dynamically adjusts assignments and ensures balance. Example use cases are distributed databases, managing partitions, replicas, and ensuring leader-follower setups for distributed databases like Apache Pinot, stream processing, orchestrating distributed tasks in frameworks like Apache Samza, search systems, dynamic rebalancing of index shards in large-scale search engines, general cluster management, applications requiring fault tolerance, load balancing, and state management. Advantages include 1. Automated state management. Reduces manual efforts by automating partition assignments and state transitions. 2. Fault tolerance. Rapid rebalancing in case of node failures ensures high availability. 3. Flexible state models. Supports predefined and custom state models, catering to diverse applications. 4. Scalable architecture. Efficiently manages large clusters with hundreds of participants and resources. 5. Zookeeper integration. Leverages Zookeeper for reliable coordination and metadata storage. Limitations include 1. Complexity. Requires a good understanding of distributed systems and Helix's concepts for effective implementation. 2. Dependency on Zookeeper. Zookeeper issues, e.g., misconfigurations, can affect Helix's operations. 3. Overhead. Running the controller and managing state transitions introduces some operational overhead. 4. Custom logic. Applications with unique requirements may need custom state models, which require additional effort. Thanks for watching. I wish you a Merry Christmas and Happy New Year. For more tech interview materials, please visit bowsy8.com.
Apache Samza is a distributed stream processing framework designed for processing real-time data streams. Developed by LinkedIn, Samza is tightly integrated with Apache Kafka for messaging and Apache Hadoop for storage. It enables scalable, fault-tolerant, and stateful processing of data streams with low latency. For more tech interview materials, please visit our website bowsy8.com. Core components include 1. Stream processing. Processes continuous streams of data in real-time or near real-time. 2. Task scheduler. Manages task execution and resource allocation, ensuring workload distribution across the cluster. 3. State management. Uses RocksDB or other backends for storing local state, enabling stateful stream processing. 4. Message broker integration. Typically uses Apache Kafka to consume and publish data streams. 5. Processing model. Implements a high-level API for defining processing logic in a distributed environment. 6. Fault tolerance. Leverages Kafka and state snapshots to recover from failures. What happens under the hood? 1. Data ingestion. Data streams flow into Kafka topics or other message brokers, which act as input sources. 2. Task assignment. Samza divides processing into tasks, each operating on a partition of the input data stream. 3. Stateful processing. Tasks maintain local state for aggregations or joins, stored in RocksDB for fast access. 4. Fault recovery. In case of failure, Samza reassigns tasks to another worker and restores state from Kafka or snapshots. 5. Stream transformation. Performs operations like map, filter, join, and aggregation on the streams. 6. Output streams. Processes results and writes them back to Kafka topics or other output destinations. Example use cases are log processing, real-time transformation and analytics of server logs, recommendation systems, processing user behavior streams to deliver personalized recommendations, monitoring and alerting, analyzing sensor data for anomaly detection or alert generation, data enrichment, joining streams with static data for real-time enrichment. Advantages include 1. Low latency, designed for near real-time stream processing. 2. Fault tolerance, recovers from failures using Kafka's built-in reliability and state snapshots. 3. Scalability, easily scales with the addition of workers. 4. State management, local state enables efficient stateful stream processing. 5. Integration, seamlessly works with Kafka, Hadoop, and other data ecosystems. Limitations include 1. Dependency on Kafka. Best performance is achieved only when Kafka is used as the message broker. 2. Complexity, requires knowledge of stream processing, distributed systems, and state management. 3. Limited ecosystem. Compared to frameworks like Apache Flink or Spark Streaming, Samza has fewer third-party integrations. 4. Resource-intensive. Stateful processing can demand significant memory and storage resources. Thanks for watching. For more tech interview materials, please visit bowz8.com. Apache Parquet is a columnar storage format optimized for big data analytics and processing. It is designed to store data efficiently, enabling fast querying and analysis in systems like Apache Hadoop, Spark, Hive, and Presto. Parquet's columnar nature makes it ideal for reading only the required data, reducing I/O and computational overhead. For more tech interview materials, please visit our website bowz8.com. Core components include 1. Columnar storage. Data is stored column-wise, allowing efficient access to specific columns instead of reading entire rows. 2. Schema. Uses protocol buffers to define and enforce a schema. This ensures compatibility across systems while maintaining data integrity. 3. Data pages. Each column chunk is divided into pages containing metadata, e.g., data types, and the actual encoded data. 4. Compression. Supports multiple compression algorithms such as Snappy, GZP, and LZO, reducing storage requirements. 5. File structure. Includes a header, column metadata, and a footer that provides fast indexing and enables random access to data. 6. Encodings. Employs techniques like dictionary encoding and run length encoding to reduce storage footprint and improve query performance. What happens under the hood? 1. Data ingestion. Data is written into Parquet format via libraries in frameworks like Hadoop or Spark. Columns are stored contiguously for better compression and I/O efficiency. 2. Columnar access. Query engines retrieve only the required columns, skipping irrelevant ones to minimize data scans. 3. Schema enforcement. Schema metadata ensures data consistency and compatibility across applications. 4. Optimized compression. Columns with similar data types are compressed together, yielding higher compression ratios compared to row-based storage. 5. Indexing and metadata. Metadata in the footer allows fast column and row group access without scanning the entire file. Example use cases are data warehousing. Efficient storage of large datasets for querying and analytics platforms like Hive and Presto. Log analysis. Storing logs in a compressed and query-friendly format for quick analysis using Spark. ETL pipelines. Intermediate storage in ETL workflows for transformations and aggregations. Machine learning. storing pre-processed feature datasets for model training. Advantages include 1. Efficiency. Columnar format reduces storage size and improves query performance. 2. Compression. Advanced compression techniques save disk space without compromising speed. 3. Interoperability. Supported by multiple big data tools, including Spark, Hive, and Presto. 4. Schema evolution. Supports adding, removing, or modifying columns without breaking compatibility. 5. Random access. Metadata enables fast retrieval of specific columns or rows. Limitations include 1. Write overheads. Writing data to Parquet is slower due to compression and encoding. 2. Complexity for small files. Inefficient for storing small files due to its metadata overhead. 3. Learning curve. Requires understanding columnar formats and encoding for effective use. 4. Row-based use cases. Suboptimal for frequent row-level updates or inserts. Thanks for watching. For more tech interview materials, please visit bowz8.com.